Then we have methanol, nitrophenol, phenol, and 4-nitrobenzoic acid. Okay, in this case, I have the names. Not necessarily I have the names of the taste, and we have the structure. But it's better to draw the structure, okay, if you don't have it. 4-nitrophenol, right? Okay, then you have phenol, correct? And then we have hydrochloric acid, HCl, which one was powerful. And then I have benzoic acid. So I have OH, 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 and OH. All of them, they have in common OH, so I cannot get rid of any of them yet. All of them are OH acids, correct? If I have an NH acid, then I will say this is less acidic, because NH is less than OH, correct? Okay, so all of them are OH. Then I say, which one is more acidic from the ones that I have? Methanol or nitrophenol, phenol, or nitro-benzoic acid. Which one is more acidic? Methanol, phenol, or benzoic acid? You see what I mean? Chemistry doesn't have to be that hard. Fine. Right? Again, hydrogen chloride because it's mineral acid. You don't see any carbons there, you see? Okay, more than. Okay, now I have methanol, phenol, one with a nitro and one without the nitro. Which one is more acidic? Phenol or methanol? Phenol or methanol? Phenol, right? Because the conjugate base is in resonance, correct? Yes? Very good. So I will have that one. Which one is more? The one with the nitro or without the nitro? With the nitro, exactly. We saw that in class. So it will be 2, right? And then 3, correct? And then 1. Okay? So 4, 5, 2, 3, 1. 4, 5, 2, 3, 1 is B. Right? Yes? Good? Okay, good. Okay, very good. Okay, lactone we have skitton C replaces that. So correct? And then that one inserts taking the place of that one. So go from 5-member ring to a 6-member ring, right? So the product is the primary amine with the 3 carbons, right? That is Gabriel synthesis, right? Yes? Okay. Will a secondary amine give me a diazonium? Will a secondary amine give me diazonium? Will I get a diazonium? Forget about the temperature here, but will it give me a diazonium? Diazonium is only for primary amine. This is a secondary amine, okay? So secondary amine is going to react with this HONO, this form HONO, decomposes into NO, and NO reacts with that. So we're going to have okay, that it just attaches to the nitrogen, and that doesn't go anywhere else, right? It's NO, N-nitrogen, right? Yes? Remember that? Okay. Diazonium. Okay? And then the second step is to actually react it with N-dimethylamine. We use N-dimethylamine on the notes, but this one has just ethyl. This reacts the same way. So this is going to react para, right? And we are going to have, notice that this reacts here. You should leave this alone. Leave this alone. It reacts here. So you're going to put your ethyl group. Notice your ethyl group is still there. N, those one N, and then this one. Got it? Okay. Yeah. Yes, and that is an exodiol, correct? Yes. Okay. We are reviewing, and in this reviewing it helps you a lot because you are already more prepared than if you were not here doing this. Right? We are reviewing and they say that makes sense, that doesn't make sense, you know. Alright? This one is actually dealing with the last topic we discussed. It's better if we draw it this way. Okay, minus water and connect, right? So after one, we do a chlorosulfonation. Remember that here we are going to lose water. Okay? That's like a sulfonation, but it's a variation of it, right? Okay? Then we are going to react that one with that myamine, right? So this one will kick up the chlorine. Alright? Of course, you know, I'm going to put cleaning, right? To catch the acid. Okay, and of course you also have the auto product, okay? Yeah, because the group is an also para director. Good? Got it? Yeah, and that we covered that today, right? The last portion of the sulfa was to hydrolyze that one, correct? Under acidic conditions and then quench it with sodium bicarbonate to avoid the protonation of this hydrogen. Right? Good? Okay. Let's see. Okay, page 52. Right? We almost finished with one of those tests. Okay? We can go through an NMR and do NMRs. Remember that in NMRs is all about putting the pieces together, right? Yes. So, and it's just about practicing. I'm just letting you know. And then that acid chloride, right? Okay, so in right? Alright? Yes? Okay, so count the carbons, okay? I don't want you to take things for granted. 7 carbons, 8 carbons. Alright? So I need to introduce one more carbon, right? And there is an easy way you have to introduce one carbon. Yes? You do the nitrile, exactly. So you do sodium cyanide. You add your extra carbon, right? That's a carbon that you need to get in. CN, right? 6, 7, 8. And then that's a reduction. A couple of ways you can do it. Catalytic hydrogenation with nickel or lithium aluminum hydride. Okay, yeah. Yes, if you can see like the synthesis of amines are repetitive. We see reactions, you know, right? Correct, you have an idea what to do. Very population. Twice the carbon, right? Give me the formula, +2 minus the hydrogen, correct? 14. And the oxygen is not on the formula, all divided by 2. Twice the carbon, which is 7. 14 and 14 cancel out, so this one is equal to 2 over 2 equal 1. Right? So there is only one unsaturation, meaning that I have a ring. I have a ring, or I have a carbon-carbon double bond, or carbon double bond up. Those are the options because I have oxygen. The double bond can be to the carbon, oxygen, or to the carbon-carbon. Right? And once you have the carbonyl, you say that's your unsaturation. That's the unsaturation. So I don't look for another ring or for carbon-carbon double bond, right? I have the unsaturation already. So, and that has 2 bonds missing. Then you are going to do this. You are not going to connect like crazy, all kinds of stuff. The oxygen forms 2 bonds and it already has it. So you're not going to connect anything here. This one connected to two things because it has to have 4 bonds, right? That's the way you do it. So you don't have an oxygen with 4 groups, right? Or a carbon with 3 and a carbon with 5, etc. Right? Okay. Now, is that only one, right? I don't even know how to solve it. Okay. Now, we have 9 hydrogens just like the test that you just had, right? So we're going to have CH3, CH3, and CH3. So I have 3 carbons there, and then over here, I don't even know how to do this. I made a mistake. If that is correct, sorry, what were you going to say? We don't know yet. It's possible, that's a possibility, right? That's a possibility. But we need to count our carbons, correct? Okay, so this one necessarily has to be, because it cannot be OH twice, it has to be CH2, correct? So we're going to say CH2, and this one has to be CH3, correct? CH3. Got it? I think we almost got it. Okay, count carbons, count carbons. There you go. You see, it's a very simple puzzle, right? CH2, 2 bonds. CH3, 1 bond. Carbon, 2 bonds. CH3, 1 bond. 1, 2, 3, 4, 5, 6. I need 1 more carbon. What is that carbon? A quaternary carbon. Therefore, it can be a terbutyl group. I use it to connect those 3. These 3 methyl groups have to be equivalent. Right? And in a terbutyl group, they are equivalent. So, that's what I do. I have my terbutyl, correct? And I have 1 bond. Right? I have 1 bond. So then I need to connect the rest, correct? Now, notice that this one has to go at the end. Or I can do this, look. I'm going to put it first like this. Right? That one goes in the middle, that goes in the middle, and that one goes at the end. Okay? Are you following? Are you following? Right? So this methyl group at the end, right? Because it's 1 bond. They don't go in the middle. Don't try to put them in the middle. Okay? Now, I have 2 options. Okay? You're not just gonna answer for answering. You're gonna try both. You're going to say, I'm done. I'm going to say, not so fast. Okay? So, the methyl group was the worst, correct? And then, you created that, right? Yeah, I created that, and now I don't know what to do. What do I do? Huh? Bromine. I can remember sodium cyanide doesn't work on a hill. I put a nitro.
She said they look good.
MGBR.
I think.
Yeah, MGBR.
Any ideas? Yeah.
Wait, MGBR?
NGBR.
Yeah.
To get a carboxylic acid.
Oh.
But then you have to transform the carboxylic acid to the cyanide. There is a way, though. Then what should I do next?
I'm gonna put that in the letter, right?
Should I do another nitration? It seems like that's about the only way I can do it.
You know what gentle mouse is?
Alright. Okay, yeah. And then what do I do?
220. 220. That's the word.
Reduce it, right? Form a very weird diazonium.
You want to see it? Okay.
I really cannot think of another one, but I'm sure in the answer key I have another answer.
Wait.
Okay. So basically sexes, right? Or two equivalents. All right. Okay. One NMR and we go. Okay. One NMR, we go. Yes. Okay. Let's do one NMR. We have a dicarboxylic acid compound because I have 4 oxygens, and those hydrogens necessarily are equivalent. So you need 2 of those. Get it? Right? If it was only 1 hydrogen, then you put only 1, but we have 2. And that accounts for the 4 oxygens and the 2 saturations. Right? And if this one has 1 bond, alright, then we go here. We say CH4, or what is this one going to be? Can I say CH4? Can I connect anything to CH4? No. And then if they have to be equivalent, and the only way, 2 times CH2. Okay, you are going to draw it. 2 times CH2. Right? And each one of that CH2 is connected to something in order to be a quartet. This is a quartet. Correct? So you say n plus 1 equals 4. You see? N plus 1 equals 4. So n equals 3. N equals 3. So means that the CH2 is connected to CH3, right? So I say CH2 connect to CH3. Since I have 4 of those, I'm going to say times 2. Right? Correct? Times 2, right? And then the other 6 things are here. I'm giving 6 hydrogens. So that one is those 2 CH3s, correct? And we already know that you have to integrate because this one will be connected to your CH2 in order to get triplet, right? N plus 1 equals 3, triplet, N equals 2 connects to a CH2. Right? So you have 2 CH2, okay, let's put it here. 1, right? 1, carboxylic acid. 1, carboxylic acid. Okay? And then count the carbons. 1, 2, 3, 4, 5, 6. How many we have? 7. And we already see this scenario. When we don't have more carbons to assign, it's because the carbon has no hydrogens. Then, since all of these ones have only 1 bond, then you connect them. And then the ethyl groups are equivalent and the 2 carboxylic groups are equivalent. Right? And then you have your triplet for 6 hydrogen, your quartet for 4 hydrogen, and your singlet for 2 hydrogen. Okay? And then you can put in the skeletal. Let's see how we do the skeletal. Okay? A, B, and C. Got it? Yeah? Okay? Then follow the reaction. Acid chloride. Then you're going to say, I make an acid chloride. Okay? And then do the next reaction. 4-methylphenol. Right? And then all we have to do, that one is 2 equivalents, 1 equivalent here and the other equivalent here. Right? Okay, let's try.
It's not that cool.
Like after the recording, it's going to be project.
What's the socials? We can't.
Okay, so I have a diester, right? Yes. And all I have to do is just, okay. Oxygen donating or withdrawing? What is the oxygen there? Next to the ring is donating. So these electrons are electron rich or electron poor? Electron rich or electron poor? Electron rich. Electron rich go. Electron rich that way. Electron poor go this way. Correct? So you may think because of the oxygen is this one, but no, it's that one. This is B, and this is A, correct? A, B, and then I do the same to the other side. A, B. No, hold on. B, sorry. B, A. B, A, next to oxygen. Okay, then I have my 6 hydrogen singlet, which is this one. C. B is my CH2. I can't ever put like these monsters, okay? I like making these big molecules, but you know I try to make it small, right? But it's the same thing, whether you're doing with 2 functional groups or with 1 functional group. Okay, good.